In this lecture I will be concentrating on a very important aspect of material synthesis, that is through hydrothermal route. And hydrothermal synthesis is a very important technique because it combines the principle of both chemistry as well as physical approach, where we are trying to use chemical routes but incorporating high pressures. So this is one technique which is 50-50 of both physical as well as chemical approach. Therefore, I have dedicated one full lecture on this to understand the principle behind it, how we can fine tune, and the scope of this method, which has not only been used for lab scale synthesis but also has gone into tons of material synthesis in the past few decades. As I have pointed out, hydrothermal is a high pressure synthesis. Therefore, the moment you think about high pressure, you think of a bomb or a enclosure. In other words, you do the reaction in a confined system, closed system. Therefore, high pressures will be generated from within, and this is another cartoon which we will see down through the slides. The specificity of hydrothermal route by which one can aim for a particular morphology of a crystal and then you can get it. And also, if you want to grow crystals, this is one of the facile route by which you can grow single crystals. As you would see, this is one of the gemstone which is prepared with near perfection, and hydrothermal can therefore be used for scalability also. It is not just limited to lab scale approach. Now, where does hydrothermal synthesis stands? If you look at the conventional methods for fine ceramic powders, the top down approach is the mechanical milling, where you start from powders of irregular size and shape, and then you ball mill it and try to get it in nano size. And then comes the chemistry routes, a long list of chemistry routes where precipitation or thermal decomposition of different natures can help in making materials. And as you would see here, hydrothermal itself now transcends to be an area of research because of the facile nature by which we can modulate the synthesis. And on the right side, this cartoon shows a list of hydrothermal synthesis that has emerged over the years. As you would see, this is an endless result. You can start with just crystal growth, and we often think hydrothermal is to initiate a crystal growth or crystallization process, but it is much more than that. You can actually do hydrothermal treatment, do dehydration, extraction, that is leaching from minerals. Then you can also attempt for hydrothermal sintering. We can do hydrothermal oxidation, and decomposition reactions can be done, and then hydrothermal electrochemical, mechanochemical reactions can also be engineered. And over the years, the usefulness of hydrothermal process has also transcended to a fusion of two different approaches. For example, hydrothermal ultrasonic, hydrothermal microwave reactions are also aimed, so that whatever target compounds that we have, it is very easy to prepare if you can integrate two different approaches. And then of course you also have this melting and rapid quenching, which is nothing but crystal growth technique, which we will also see in one of our lectures. So as you would see here, this is a endless route, and there are a lot of combinations that are possible. And as we record this lecture today, a decade from now, hydrothermal can transcend to other various avenues also. So we will just look at few examples. First of all, the principles of hydrothermal growth or hydrothermal process, and then take specific examples to understand what are its limitation and what is the landscape of this hydrothermal process. To start with, let us say hydrothermal synthesis is all about the reactants are dissolved or placed in water or another solvent. If you put it in some solvent, organic or inorganic solvents, then you call that as solvothermal. you call it hydrothermal if you just use water, or you can use water with some additives, that is also called as solvothermal in one sense. Now you put the whole thing in a bomb, and this is actually a metal, outer surface is a metal, but then what you see inside can be a bomb with Teflon containers. Therefore, this is not the container by itself, this is a bomb to just control and release, and through this orifice you can also try to leak out a gas, so that it is not a if it is not a controlled closed vessel reaction, it can turn out to be a bomb. Therefore, you can actually release it with a small diaphragm which can actually leak out excess pressure. So, this is the simplest way we can define a hydrothermal reaction, and this bomb is heated above the boiling point of the liquid, either solvent or water, so that you reach its supercriticality, and we can also try to do this heating in a conventional furnace, or we can do have a special arrangement by which we can heat it inside, or we can engineer it in a more sophisticated way nowadays using microwave oven. And commercially tons of zeolites being made by hydrothermal process, mainly because making zeolites or cage structures is a very challenging work or very challenging attempt, and therefore expertise is needed to get the size and shape control of the end product. So, zeolites, I will show one example of how this has made inroads into application, but we can actually talk in terms of tons of zeolites can be made using such autoclaves. Now, what are the conditions? Solvent, whether it is water or any other solvent, it is taken to its boiling point, and usually some basic solvents are also added, like sodium hydroxide, potassium hydroxide. So, most of the reactions are done in basic conditions, and this particular method is also used for making nano oxides. For example, simple oxides or substituted ones, layered oxides can be transformed into nano wires or tubes, and then carbon nanotubes has been formed this way, and some elemental nanostructures also has been attempted. So, this is not just confined to bulk material, but also nanomaterials. Now, when we look at the phase diagram and then look at how we get into this critical point, as we heat the autoclave, now water actually will show different density, and as a function of temperature, as you would see at low temperatures or at room temperature, the density of water is 1, but as we heat the water, you have a competition between the liquid phase and the gas phase, and at precisely 374.15, which is the critical temperature of water, you can achieve this critical point with a density of 0.321. So, density or the viscosity of your water will change with temperature. So, the water at 300 degree C will have a density of 0.75 gram per cc for the liquid phase, and for the gas phase it will be 0.05 gram per centimeter cube. So, above the critical temperature and critical pressure, you have this supercritical and fluid phase. So, this is the critical point that we try to achieve in the bomb or in the autoclave. When we think of solvothermal reactions, there are some general aspects that we can have in mind. Usually more material can be dissolved at high temperatures, therefore, we slowly increase the temperature in the bomb, and the properties of the water also changes along with the material that we are dissolving. For example, with increasing temperature, the ionic product increases, viscosity will decrease, and the polarity will decrease but with pressure polarity of water, that is the dielectric constant, will also change. As a result, the reaction of water itself, behavior of water itself will be different in its critical temperature. So, synthesis is usually in closed vessels. So, all three parameters become very crucial. So, they are interdependent. We cannot just simply worry about the temperature and pressure, because volume is a intrinsic stuff which is involved there. Therefore, volume plays a very critical role in modifying the dynamics of hydrothermal process. There are two methods by which we can do this. One is isothermal, mainly for powder synthesis, where you just take the reaction temperature to 70 degrees or 100 degrees and put this in a furnace for 3 days, 6 days and 7 days and so on. So, recrystallization, for example, recrystallization oriented powder synthesis usually involves a long period of time, and those are isothermal experiments. And then you also have temperature gradient experiments. Usually if you want to grow a crystal, you try to seed a crystal and then slightly try to provide a temperature gradient. So, as you are going to pull it for over a period of time, these crystals will start growing on the seed crystals and you get huge crystals. We will see some examples later. So, in solvothermal synthesis, a typical single crystal that is formed is shown here. Synthesis from liquids above boiling point at 1 bar is usually realized. Hydrothermal or solvothermal reactions, as we see, water is usually used, or we can also use ammonia, some mineral acids can be used, even carbon dioxide and SO2 can be used. And these days, because of green chemistry, supercritical carbon dioxide is now taking more attention than even hydrothermal process, because carbon dioxide in its critical state can become a very good solvent also. So, this is actually becoming a prime focus in green chemistry, and also you can see alcohols which can perform the job. If we are aiming for sulfides, then H2S gas can be used. So, a variety of solvents can be used. Ammonia is a common solvent and carbon dioxide is becoming important. So, in hydrothermal crystallization, we are actually aiming for large crystals and gemstones. This is how it is made, and in hydrothermal synthesis, by and large we are talking about preparing powder samples of oxides. When we talk about leaching, take ore and then try to leach it with treatment with some alkali. For example, alumina, you try to take bauxite ore and then try to leach it with sodium hydroxide, then you will be able to get Al2O3 on calcination. So, this is one way you can try to do a leaching. So, several things can happen in the bomb, and we can see some of the issues in the slides. One of the prime criteria for hydrothermal synthesis is the pressure temperature diagram, which is very important, and we need to know what is the loading factor that will give you the optimum pressure that you are looking for. The autogenous pressure in a closed vessel can achieve different proportions depending on the filling. For example, if we are talking about 32% filling of water in a autoclave, then it will expand as you increase the temperature. It will fill the autoclave at the critical temperature. At higher filling degrees, the water will expand to fill the autoclave at temperatures below the critical temperature. So, this will actually result in a steep increase in pressure inside the autoclave due to differences in compressibility of gas and liquid. For example, you take the case of 80% filling of autoclave, then at 245 degrees C, we are somewhere here, we can actually blow up the autoclave. So, optimum filling is somewhere around 20-30, where you see the pressure is not steeply increasing, it is moderately increasing, therefore you have a fine control over the pressure buildup inside the vessel. So this pressure versus temperature plot gives you an idea. Suppose I am going to take only 10% of the filling, then I can play around with this whole regime of temperature, because the pressure that is achieved is highly controllable. So depending on the volume of the pressure vessel that you are taking, and depending on the nature of oxide that we are trying to prepare, we can play around with any one of this parameter. So this is a guideline to ascertain whether you are in a safe zone. So if we happily try to fill the pressure vessel with 80 or 70%, then even at 200 degrees C you will be generating very high pressures, where the pressure vessel cannot stand such a pressure. So we should be beware of gas evolving or low boiling 7, which can increase the pressure at a given temperature. So we should also understand that the starting materials by itself should not release extra gases apart from the pressure that we are generating. So during the reaction, if some decomposition process is happening and that is going to release some more of gas, then that will add up to the inherent pressure that is getting built up. Therefore we should be cautious, or a back calculation is needed as to how much of starting material on heating at what temperature will give what amount of pressure. So all this has to be calculated. So pressure and temperature along with the volume is a very governing criteria. So this is a useful information that one should know, but in some cases hydrothermal process is very reluctantly progressing, mainly because it needs some amount of catalyzing agent, which we call it as mineralizers. Such mineralizers are usually needed for the crystallization to occur. The solubility of the materials is not always sufficient, so mineralizers are generally used for crystallization process. The best examples of such mineralizers are either some alkali fluorides, alkali hydroxides, alkali metal hydroxides, which can do the job. For example, quartz is synthesized in a temperature gradient at 1 kilobar. The solubility is too low for efficient crystallization. As a result, several mineralizers are added to improve on the solubility of SiO2. So if you want to make some silicates or zeolites, just taking pure silica in water is not sufficient. Therefore you can put any of this mineralizer. As you can see here, solubility is going to increase very rapidly if you are going to work out with sodium hydroxide, and again the molarity of the hydroxides also matter in increasing the solubility of SiO2. So you can see a variety of combinations there. For example, zinc sulfide you want to grow, then potassium hydroxide is a very good candidate. Zinc oxide, if you want to go, sodium peroxide hydroxide is a very good mineralizer, and alumina also requires such mineralizers for formation. So solubility as a function of hydroxide concentration is a very useful parameter to know, because this can enhance the process to a greater extent. When we think about growing large crystals, then in a typical autoclave you need to have a temperature gradients, and this is how it is. We will come to this scheme later, but generally you need to have a temperature gradient where you take the nutrients, which is nothing but your starting material, and then these are the seed crystals which is hanging there, and there is a orifice which will prevent actually the particle flow, which is the secondary nucleation, from occurring. Therefore the seed crystals are in a temperature gradient zone where slowly this mineralizes these nutrients will actually propagate through this baffle, and then larger crystals will start growing. So this is another way of making the larger crystals, and typical requirements are you need to have some weight percent solubility ranging from 0.001 to 0.1 weight percent, and the temperature in the growth zone has to be lower than the dissolution zone, otherwise you cannot create a progressive temperature gradients, and the convection transport the hot liquid up to the growth zone, which is the way these seed crystals start acting as nucleation sites for larger crystals to grow. There are some problems also where a retrograde solubility is also encountered, especially if you take the case of silica in pure water, and in some salt solutions at higher temperatures you would see the solubility actually would come down. So, this also has to be noted. You take the case of silica in pure water above 350 degree C, as you would see here, as you keep on increasing the solubility at very low pressures, you would see increase in solubility and then it is coming down. So, this range is a retrograde solubility. Therefore, when you are trying to go to very high temperatures, then you need to have a compromise with the pressure in build up inside the bomb, otherwise you would not be getting the end product. So, we need to have some idea about these phase diagrams where you would know what is the temperature at which I should play and what is the optimum pressure that is required for the quartz for example to grow quartz. So, this is a very useful parameter that one should have in mind, and we can also have similar calibrations made for halides and carbonates as mineralizers. There are also other solvents other than what I have mentioned depending on the end product that we are looking for. For example, if we are talking about amides, nitrates, then ammonia as a solvent is a very good option. If you are looking for sulfides or elemental compounds, then we can think of carbon disulfide or CCl4. These are all useful materials for making a specific end product, and if we are looking for sulfides, for example, H2S is usually the preferred solvent, dissolved in an organic solvent can play a vital role, and we also have several other brominating and chlorinating agents like thionyl chloride and so on, which can be used for chlorinating transition metal oxides. So, apart from water and organic solvents, we can also have flexibility with other solvents such as this. Also, this list gives you an idea what is the critical temperature of various solvents that we are using. As you see, for water the critical temperature is 374 degrees centigrade, where you can achieve up to 220 bar atmosphere. So, this is as far as water is concerned. One of the reason why carbon dioxide is more preferred is you do not have such a great critical temperature. So, even very close to room temperature you should be able to get a supercritical carbon dioxide with the very high pressure, that is 73 bars, and again you can see some examples of ethanol and methanol. They have a critical temperature 243, 240, and here again you can go for very high pressures, and in this whole thing you would see for achieving high pressures water is a very critical component or solvent. Now, just want to take you back into little bit of the history and show some examples of the earlier work before we go into examples. Hydrothermal synthesis was first explored in 1845 by Schaffholt, was the first one to make quartz microcrystals, and then using glass tubes as pressure vessels. Bunsen in 1848 he made some carbonates as crystals, and then on there has been several activity, and the most important one is 1943 by Nacken, who actually used hydrothermal synthesis for industrial production of quartz, and this was the first time the introduction of hydrothermal synthesis was taken seriously. And then there has been several books written where the mechanism and the physical implications of hydrothermal synthesis has been studied. So, this was mostly a turning point where hydrothermal synthesis was taken much more seriously. Just to draw your attention, this piezoelectric properties of quartz was discovered in 1880, and the world production of quartz was aimed in 1985, and up to 1500 tons of quartz has been made using hydrothermal synthesis. Today we do not have just small pressure vessels what I showed you. Now big autoclaves are there which can help us in doing the scale up operations. So, this is little bit of the history of this hydrothermal process, and these are some of the old photographs that tells you how big the autoclaves can be. And this is not the autoclave, this is actually the seed which was inserted inside. So, the autoclave is actually housed here at the floor level, but this is the seed crystal which is actually lifted. You can see that this is hanging, and all these white slabs what you are seeing is nothing but a quartz crystal, and these quartz crystals are grown over a period of months to grow into huge size, and this is the dimension of the seed crystal in front of a small boy who is taking a look at it. And such quality industrial grown quartz crystals have find useful applications in many fields, especially in electronics, in watches, in optical equipments like laser windows, prisms. All these variety of industrial applications have been engineered with large quantity of quartz crystals, and typically the process that occurs is shown here. Those big blocks of quartz are actually precipitating on this seed crystals which is kept here, and this is being pulled upward, say 1 millimeter per hour or 1 millimeter per 2 hours, that is the rotation at which it is slowly done. Therefore, it runs into several days and months before the whole thing is actually pulled out. So, the temperature zone is somewhere here, this is the temperature zone, and this is mechanically pulled. So, it is not done manually, it is mechanically pulled at a very slow rate. To our naked eye you would not see any movement at all, but that is the way it is engineered. So, once you do a slow pulling, then a large crystal can be isolated from this. So, to grow very big crystals you need a big loading unit also, because you need so much of starting material. Therefore, a big autoclave like this can be made, and as you see here, to hold the pressure, this is actually done with a lot of huge nuts and bolts. Therefore, this is a real scale up process, and some of the hydrothermal crystals which have been grown in the past, this is zinc crystals, and then emerald crystals have been grown, and we also have calcite, calcium carbonate crystals have been grown using this procedure. As you can see, big size crystals can be engineered, it is not just for lab scale synthesis alone. Advantages of hydrothermal synthesis, usually we are playing around with the moderate temperatures. You do not need very high temperature, because at this temperature you are almost achieving the supercritical temperature of any of the solvents. Therefore, this is a safe range, and as a result this can even be experimented in lab scale. And some advantages of hydrothermal synthesis is it is possible to synthesize materials below a transformation temperature. For example, this is the transformation temperature of gamma copper iodide, and because we are using temperatures below 300, we can easily stabilize this. Or for quartz, the transition temperature alpha to beta is at 580, therefore at low temperatures you can actually stabilize one of the phases. And again, one other important aspect, I will come to this slide later. Chromium dioxide is a very useful videotape material. It is a ferromagnetic metal, and starting from chromium oxide you can prepare CrO2, and as you do this synthesis you will also release oxygen. Therefore, there is a inbuilt pressure that is released during this hydrothermal synthesis. What is peculiar here is chromium is usually stable in either chromium 6 or chromium 3, but in hydrothermal synthesis you can actually get chromium 4 as a metastable phase. So, CrO2 is not easy to prepare by any other technique other than hydrothermal. In fact, large scale synthesis of chromium dioxide has only been achieved using the only technique, that is hydrothermal. No other technique has given such precise control over the oxidation state. And then preparation of metastable phases we can try to achieve. And one of the other very useful parameter or very useful implication of hydrothermal synthesis is control of the zeolite morphology. We can make cage structures using hydrothermal approach. Comparing zeolite synthesis with biological process, we should understand how much we are blessed with the mother nature, because we tend to realize this with sophisticated cage structures of aluminosilicates using hydrothermal process, but a simple comparison between how this can be easily done biologically will give us some clue what the biological process means in material synthesis. For example, take the case of zeolites, it will take days together if you are going to use hydrothermal process, whereas this will just happen in few hours. Concentration of this inorganic precursors, very harsh environment, whereas very dilute concentration is enough, and the pH conditions although comparable, now you can achieve using biological process at room temperature the same zeolites can be formed. So, we are trying a very hard way to synthesize some unusual inorganic structures, but at the same time mother nature has gifted with a lot of bacterial based or enzymatic based reactions which can actually stabilize such very novel motifs of metal oxides in a very fast way. Hydrothermal leaching, as I told you, is done by taking bauxite ore, which is nothing but aluminum hydroxide and aluminum oxyhydroxide. So, you can treat this with the sodium hydroxide concentrated solution, and they form the respective sodium aluminum hydroxide precipitates, and this can be heated to get corundum structure. So, starting with crude ore, we can go for highly pure alpha alumina phase by hydrothermal leaching. So, this is one of the important applications. I will also show you different facets of the autoclaves that are used. This is one range of autoclave where you have this sort of quartz tube which is sealed tubes, and the sealed tubes are actually kept inside a bomb or a autoclave, where you can use a secondary system like carbon dioxide. In this case we can actually use carbon dioxide, and during heating this will also grow in pressure, and this pressure will try to confine the internal pressure, otherwise this internal pressure that is generated in the seal tube will actually explode. Therefore, a compromise has to be made in the closed vessel. So, you actually use a external influence like carbon dioxide in this case to restrict the internal pressure from blowing up. So, this is usually done in a closed vessel system. We can also have an open vessel system where you do not use a seal tube. This is again a seal tube. Do not use a seal tube, you just use a open vessel like this, but you can actually block the opening with the bomb so that the pressure is actually built only here, and this is another way of generating very high pressure. So, this is called a open vessel external pressure based autoclave, and in this case you are actually using a sealed capsule and trying to generate high pressure, but at the same time you counteract that high pressure from putting another solvent to combat with the internal pressure. There is another autoclave which is a Moray autoclave, which is nothing but a bomb which is made where the whole thing is heated. The whole bomb is actually heated to high pressures and to high temperature, and this is one way of doing that. Or we can actually try to heat the vessel here with the open vessel. We can try to block this opening and then heat the vessel here, but the top portion can be actually used for cooling. Therefore, very high pressures can be avoided. So, there are two types of autoclaves that you can use for making materials, and that also depends on what sort of material that we are looking for and what is the scale up operation that we require. There are other issues also which are connected to hydrothermal synthesis. This particular cartoon tells about the EH-PH phase diagram, which gives a clue what sort of other governing parameters which we can try to operate with during the hydrothermal synthesis. By controlling the potential and the pH during hydrothermal synthesis, it is possible to specially control the oxidation state. For example, in the EH versus pH diagram here, you can clearly see that if you are planning to stabilize manganese in 2+, then we need to change the potential of the reaction mixture as well as the pH within this range, and beyond this we can encounter many other phases. For example, this is MnO2 in +4 and Mn2O3 in +3, Mn3O4 in 3 and 4 states. All these are possible when we go to very high pH. Therefore, if we need a finer control on the oxidation state, then we need to take into consideration both the pH as well as the potential that we engage with. For this reason, hydrothermal buffer systems are also used, and there are several buffers which can be used for making a precise control. For example, arrangement for the growth of magnetic ferrite crystal. These are lanthanum ferrites, lanthanum where lanthanum is the rare earth here, and Fe has to be in 3+ oxidation state, and for this reason actually a copper oxide buffer is used so that the formation of Fe2+ can be prevented. So, hydrothermal buffer systems are also play a very vital role. Now, when we come to the high temperature reaction in hydrothermal process, what really happens and how does the whole transformation occurs, because we are operating at a very low temperature to prepare high temperature phases, but we are operating at a very high pressure. So, what really happens, usually it is a liquid nucleation model that is suggested, and this model differs from solid state reaction, because in solid state synthesis it is mostly a diffusion controlled reaction where atoms do migrate between solid interface, but this is usually a liquid nucleation method that is responsible for the growth of oxides. Due to enhanced solubility of water increases with temperature, and if we are going to add alkaline solvent like hydroxide, then the solubility will dramatically increase with temperature, and thereby this nucleation process can be enhanced or moderated. If you take the case of silica and its solubility in water, as you see here, when you increase the temperature, the solubility very marginally increases and maximum solubility is aimed at 350 degrees C for silica in the growth of quartz crystals, whereas the moment you put 1, 2, 3% of ammonia into it, then the solubility of the same silica enhances to 560 or 515 grams per liter. So, solubility can be enhanced with this sort of additives. So, this is mostly a nucleation method. Now, if you take the case of barium titanate as an example, barium titanate is formed by the reaction of barium hydroxide and TiO2, and this gives BaTiO3 at a optimum temperature of 300 to 450 degrees C in hydrothermal condition. But the proposed mechanism for barium titanate formation can either be viewed in two ways. One is in situ crystallization or dissolution recrystallization. Dissolution recrystallization is where you have barium hydroxide and titania has gone into one single homogeneous phase, and from there recrystallization occurs, which comes out as barium titanate, or it could be a in situ crystallization. One of this is getting crystallized and over which the other can form into a barium titanate. So, we need to know the proof of what sort of process that is occurring, which gives you a very nice barium titanate morphology, and this is the TM picture of those barium titanates which are formed. But what we see is there are three important things that happen which is weighing or which proves as an indicator for dissolution recrystallization. Now, one thing is when varying the water isopropanol ratio in the synthesis, the grain size of barium titanate decreases when amounts of alcohol increases. So, this is one clue that tells that something is happening when the solvent is changed. Another thing is TM observations of incompletely reacted powders show that there is either it is a amorphous barium titanate phase or it is entirely a crystalline phase. You do not get to see both the cases in TM, and then in high resolution TM we also see that there is a presence of necks between particles. These three experimental observations suggest there is a strong evidence for dissolution controlled recrystallization process which is occurring, and this necking actually can be seen here, and this is the necking area between two particles, which gives more indication that this is a dissolution induced recrystallization, otherwise these two will be separated. And if it is a in situ crystallization, then the model is you would not see titania going into the solution, where the titania solubility is much less than barium hydroxide, because barium hydroxide can easily dissolve into water. So, in that case what you expect is once a seed crystal of titania is formed, then you have barium and other components coming and joining, and then overall it will transform into a barium titanate process. But what is seen is that this is not a heterogeneous crystallization process, whereas it is a complete dissolution. So, for in situ transformation what you would require is just a porous product which will act like a nucleation site, and from there the whole thing can evolve. But for dissolution precipitation, what you would see is a dissolution should be much fast to ensure a steady flow of reactants. So, by and large when we are trying to make oxides, the solubility of the starting materials, the mineralizers that you add, will decide whether this process would go by the dissolution precipitation mechanism. Again there are other useful insights that we can draw from hydrothermal process. For example, this is a TM graph which clearly shows that TiO2 wires or tubes can be formed. So, this is the way we do it. Take TiO2, dissolve it in sodium hydroxide in hydrothermal condition. Actually the crystals get rolled up into a tube or into a flake. And how does that happen? You can see this sort of a 2-dimensional sheet is evolving, but under hydrothermal condition they get wrapped up into a tube like structure or like a wire like structure. Instead of going into a 3-dimensional network, they get rolled up into cylindrical compacts, and the reason is the 2-dimensional crystal flakes have low resistance to bending in a normal approach or using a conventional approach, whereas hydrothermal energy actually curls these flakes into a tube. Therefore, usually when we try to prepare oxides, we either end up with nano wires or rods or tubes, and this is mainly because this resistance for bending is actually overcome by the high pressure. And why tubes? Because when diameter grows, the strain of the tubes is outweighed by minimizing the energy, and therefore you actually get nanotubes with these under hydrothermal conditions. And also we get very different morphologies. For example, nano flower type of a morphology is observed for zinc oxides. And why this nano flower type is coming? Because of the CTAB assisted hydrothermal reaction. CTAB is nothing but ammonium bromide with a long alkyl chain, and if we are going to put CTAB, then we see this sort of floral pattern coming, where you get a nano flower like zinc oxide rod coming, whereas if there is no mineralizer that is added, then you get separate individual particles of zinc oxide. So this is one of the clue that along with zinc hydroxide and water, if you are going to put some mineralizer, then we can get this sort of pattern emerging. And this is the SEM view graph of such nanoflowers, and this is the TEM view graph clearly showing that such nanorods can be made. I will just stop with a few examples of some of the noted oxides which can be selectively prepared using hydrothermal synthesis. One is chromium dioxide. As I already pointed out to you, chromium hydroxide is actually in 4+, which is very difficult to prepare. There are many reports nowadays where thin films have been thin film technology has been used to stabilize chromium 4+, but again there is a lack of clarity in the oxidation state of chromium. Why chromium 4 is very difficult to prepare? If you look at the temperature versus pressure phase diagram, you would see chromium oxide is actually coming in this region, and it is actually happening slightly above 400, and this is stabilized at very high pressures. So this can only be achieved by hydrothermal process, and under ambient conditions it is not possible at all. In lab scale, people have tried to use seal tubes to prepare chromium dioxide, but with great difficulty. So to prepare chromium dioxide, which is a ferromagnetic metal, it is a big challenge, and hydrothermal reaction is one way that we can do it. And these are the SEM micrographs which clearly tells how the formation of CrO2 happens, starting with the chromium oxyhydroxide CrOOH, and then when you heat it for a long time under pressure, then it transforms into CrO2 like this. And we can also try to isolate rod shaped CrO2, which is actually needed. Now if we prepare the CrO2 in lab, you would usually get a platelet or spherical shaped one, which is actually not useful for your recording media. What you need is this sort of acicular shaped crystals, which is possible only through hydrothermal route. And here again another group has also prepared chromium oxide single crystals, and you can see this shape and size selectivity that you can achieve using hydrothermal synthesis. This is a typical XRD pattern of CrO2, where you almost see a very small negligible percentage of Cr2O3 is sitting, otherwise a very clean compound can be made. and TgDTA clearly shows that these are indeed CrO2 crystals. The Tg, DTg and DTA thermograms are indicative that this CrO2 to Cr2O3 conversion occurs somewhere around 575 Kelvin. There is another report where LaCrO3 is made. This is a perovskite compound, and this is a very good heating element. Lanthanum chromate doped with strontium is a very good heating element, and you can make this sort of nice shaped crystals and single crystalline using hydrothermal process. But as you would see here, in this case there is a influence of stirring when you are trying to take aluminum hydroxide, chromium hydroxide and heat it in hydrothermal condition. With stirring you can see the crystallinity improves. So each system holds some surprise, and again if the influence of alkalinity, if you are going to take potassium hydroxide mineralizer, you would see the critical composition where pH is 8 to 9 is the place where you would really get LaCrO3 in single phase. In other cases other compounds do precipitate. So pH is a governing issue, and then stirring improves the crystallinity, and also the temperature seems to improve the crystallinity to a greater extent for LaCrO3. And then we also have a hybrid model where you use microwave hydrothermal. This was actually pioneered by Rustam Roy's group in Penn State as early as late 80s, and this is a paper published in Material Research Bulletin showing how with the different duration of microwave exposure titania particles can be prepared. And there is also a comparison made between microwave assisted hydrothermal process and conventional one. You can see here conventional hydrothermal process, it requires days or hours together, whereas in microwave engineered hydrothermal process you can speed up the whole reaction. So this is a very useful way where you can replace conventional heating times using microwave to speed up the reactions. And this is another example of how zirconia can be made. Microwave route you just hours, and the conventional route, and then we can make comparison between microwave prepared and conventional hydrothermal process. You can clearly see the particle size distribution is distinctly different between these two. And not only that, the most important or useful application of hydrothermal synthesis is preparing cage like structures, because for hostless guest chemistry, where you can put selectively some reactions or even cracking of alkanes in or some alcohols into gasoline, zeolites are used, and specially creating such cage like structures, hydrothermal synthesis has been used by and large. And not only simple oxides, complex oxides can also be prepared using hydrothermal routes. And lastly, I would like to show that hydrothermal synthesis is still the most proven method for zeolite chemistry, and zeolite chemistry has gone into a big industry now. Most of the catalysis in automobile exhaust is mainly using zeolites. Removing hardness of water is achieved using zeolites, usually starting with simple SiO4 tetrahedra. We can try to make cage like cuboid structures which has typical cage cavities, which is useful for taking selectively some gases, effluent gases or some solvents where chemical reactions can be achieved. And these are two people, Barer and Milton, who are considered to be fathers of zeolites, who first experimented the usefulness of zeolites in industrial processes. And the zeolites can actually be made using a simple progression of reaction, where you take amorphous product, dissolute, convert it into solution species, and over a period of time it will come out as a crystalline zeolite. So one of the notable zeolite even now which is used in automobile exhaust is ZSM catalyst, which is nothing but aluminum or gallium oxide doped with silicon or germanium. So, this is still proven to be one of the most powerful catalysts running into billions of dollars. So, such cage like molecules can be prepared using hydrothermal process, and here is another example of how zirconia can be made using a hydrothermal route and the various parameters that are involved which affects the structure of this zirconia is also studied using hydrothermal route, and the toughening of zirconia can be modified with the addition of yttria or alumina and so on, and the fracture toughness of these zirconias have been evaluated using hydrothermal process. Lastly, I just want to conclude by saying the pros and cons of hydrothermal synthesis. What are the advantage? One is you can discover many range of new materials, because every particular reaction will bring about a new metastable phase, easy and relatively cheap, which can be experimental in a lab scale. And the difficulties are we need to understand the chemistry that is operating. It is not just generating very high pressure, but we need to understand beforehand the nature of the components, additives that you are using. Therefore, we need to have a knowledge of how to control this morphology and size. This although range is very big, but still limited to only few materials, and it is impossible to attain variation in size with this. Therefore, the critical parameters that are involved are more than 2. Therefore, a knowledge of the starting materials, the reaction conditions like pH, pressure, temperature, volume, all these forms important ingredients in hydrothermal reaction.